This lecture introduces direction field, a method that helps us investigate the behavior of differential equations graphically. For an example, if we consider a falling object of the mass m equals to 10 kilograms and a drag coefficient gamma equals to 2 kilograms per second, then according to Newton's second law, the equation of motion becomes dv dt equals to 9.8 minus v over 5, or equivalently, it is v prime equals to 9.8 minus v over 5. So this equation here is an differential equations because it involves differential the derivative of v, and it describes the rate of change of v in terms of v, right? So the question is, where v of t is the velocity of the object with unit meters per second, t is time in seconds. Suppose this object is dropped from a height of 300 meters, find its velocity at any time t. That means finding vt, right? What is vt? So we wondering, can we investigate the behavior of this differential equations without even solving it? Well, let's look at these equations. So let's consider if there's a curve. Look at this curve vt for an example, right? And if I can pick a point on this curve right here, let's say t and v, t0, v0, right? So let's say t0, v0. And from this point, and if I have this curve, I can draw a tangent line to this curve at this point, t0, v0. Tangent line. And I just take a small segment of my tangent line to create a vector from this starting point to this terminal point. Just imagine that if you can create a lot of vectors like tangent, like slope vectors on this curve, then you can kind of imagine, you can graphically describe the solution curve of the equations. So if I pick another point, I draw another slope, right, vector, pick this point, draw another slope of this vector, or I pick this point, I can draw a slope vector here. All right. So the question is to see that once you have a lot of vectors describing these differential equations, then you can kind of see the solution curve, which is like, it's gonna serve throughout these vectors here. All right. Now look at our equations. If we consider this is the starting point and I want to graph this vector, I need the terminal point, right? How can I find the terminal point? So the terminal point here, I call it V1, T1, V1. Okay. And in order to find the terminal point, I know that the slope of this line here is V prime of T0. Okay. So I know the slope of the line is v prime of t0 equals to the slope, right, that goes through the starting point and the terminal points right here. So that would be v1 equal to v0 divided by t1 equals minus t0. And v1 equals to v0 equals t1 minus t0. It's just like the delta t, which is the difference between this point t0 and t1. All right. And again, this is just a segment of my tangent line. I can call a fixed delta t for all the vectors that I'm creating. So let's see, the delta t in this case is 0.5. I want to set the magnitude for my difference t's is 0.5. It's a fixed delta t. Then I have t prime of t0 here. then at this point, I know that V0 is given. I pick a point T0, V0. I just need to find V1 because T1 can be determined using T0 plus delta T. So V0 here equals to, according to this equation, it's just 0.5, right? Or delta T times 2 V prime T0 plus V0. And we know that V prime T0 is actually, we can find V prime by plugging the value of V. We can find V prime here to find V1. So now I know how to find the terminal point from a starting point in order to create a slope vector of my direction field. Okay. And I can replace, in general, V1 equals to delta T times V prime of T0 plus V0. Okay, again, if you have a starting point, pick a starting point, use your differential equation to find V prime, which is the slope of the tangent line, and set a fixed delta T. You can have it 0.2, 0.5, so on and so forth, to find the terminal point. Once you have the terminal point, you can create a vector by connecting the starting point with the terminal point. Create one vector at one point T0, V0 using your differential equations. Now let's use our differential equations to create some slope vectors. Okay. At this time, I want to use the point when t equals 0, v equals to 10. When t equals to 0, v equals to 10, this is the point 0, 10 right here. And using the differential equations, I found that v prime is 7.8. And using the starting point and terminal point, I found that my terminal point is 0.5 and 13.9 when the fixed delta t is 0.5. Okay. So terminal point is 0.5 right here. And then 13.9 is somewhere over here. So I just drew one slope vector at the point 0, 10 with the slope of the tangent line is 0.8 using the differential equations. And observing this differential equations, v prime here does not depend on t, it only depends on v, right? So that means as long as you have the same v value, it doesn't matter what values of t, the slope will be the same, and then your vectors, and then your slope vectors will be the same for different value of t, but the same value of v. That's what Bean says. If I look at this point right here and I want to draw a slope vector, at this point, it will be the same, the same vectors as I drew it here. I just take this vector and I move to the right. Okay. Similarly, at this point, I will have the same slope vector. Along this line, v equals to 10. Okay, I have identical slope vectors. All right, let's look at the point v equal to 49 and t equals to 0. So 50 right here, 49 probably right here. Okay. If v equals to 49, I notice that the v prime is 0. That means the tangent line is just the horizontal line. I know that the starting point is 49 and the terminal point is 0.5 and 49, but you have the same v value. So if your tangent line is just horizontal lines, that means your slope vectors are just going to be horizontal vectors. Okay. Now look at the point 0, 50. So 0, 50, I found that the v prime is negative, and then they have the starting point and the terminal points right here. So 50 is up here. Okay, I want to use a different color. So it's negative. The slope is negative. That means your slope vectors are pointing down because it's negative 0.2. Right. So these three examples here shows you that when you have different value of v, the slope of your vectors are changing, right? For some value, you have a positive slope. For some value, you have negative slope. For some value, you would have a horizontal or 0, the slope of 0. Okay. So if you repeat this process for a lot different v values, you're creating a direction field for this differential equations. Okay, just repeat this process for a lot more v values, like v equals 80, v equals 70, right? V equals 5, v equals 30s, so on and so forth. Then you're creating a direction field or slope field. Here. So one should use a, so you can create, for sure you can create slope field by hands, right? By drawing a lot of vectors like this, or you can use a software to create it, a slope field. So I use a software to create this slope field. And this is the slope field or the direction field of the equation that we are looking at right now, right? V prime equals to 9.8 minus V divided by 5. Okay. And you can see that along the line, when V equals 2, so this should be, in this case, this is T, right? In this case, this is V. All right. Along the line, V equals to 49 right here. You have a horizontal vector slope, slope vectors, right? Horizontal slope vectors, and you have like negative slope right here, and you have like positive slope right here. And this curve here is one of the solution curve. Or you can call it as a trajectory or solution curve. Okay, this solution curve is a solution curve when this is the initial value. So the initial value of this solution curve in this picture should be V0. When t equal to 0, V equals to 8 is the initial value, right? So here's the definitions a slope field for the first order differential equations, y prime equals to a functions of x and y, where x is the independent value and y is the dependent value, and y prime is just the derivative of the dependent value y, is a field of short lines or arrows of slope, right? F, xi, yi, where xi, yi is a point on this xi, xy plane. So this is a xi plane. Draw through each point xy, or alternatively with the tail of the arrow at xy. Okay. So slope fields show graphically solution curves or trajectories flow through the plane xy. So here's an example of some solution curve. So I have another solution curve here. I have a solution curve here, which is just a straight line. This curve will tell you that if t equals to when v equals to 49, right? When you start at a point v equals to 49, then the derivative of the equations, or the accelerations, the derivative accelerations v prime here will be just 0. So if you plug v equals to 49, then v prime equals to 0, right? If you start at this point, then the object is not, the velocity of the object is not moving, it's not changing, it's just gonna be just a straight line. And later on, you will learn that v equals to 49 is the equilibrium point. Okay. All right, you have a solution curve right here. And remember, in this example, we just drop an object. That means the initial points we start is when t equal to 0 and v equal to 0. This is our initial value, right? And the solution curve for this here should look something like this. So all these solution curves are never intersect each other. They would just they approach into the equilibrium line right here, but they would never intersect. Any two solution curves would not intersect each other. So if you want to solve this equation analytically, in section 2.2, you can solve this equation, and then the solution for the equation is Vt equals to 49 plus C times e to the negative t over 5. And then you given the initial velocity, initial value, at t equal to 0, v equals to 0, then the particular solutions is c gonna be just 1, right? You're gonna plug -1, and you're gonna plug t equals to 0, v equals to 0, you solve for c, and then this is your particular solution. V of t equals to 49, parenthesis 1 minus e to the negative t over 5, and it should be in a meter per second. Is your unit. All right. So this is the analytic solutions, and this is how it looks like using direction field. You can look like this is one of solution curve here. If it starts at 0, then the solution curve should look like this. This is exponential functions. All right. Now, if we want to do an exercise, like this is the matching problem. So you're given 3 different solutions, 3 different direction fields here, and you want to match this direction field to its differential equations, right? So if I look at the first direction field, this one right here, Well, I can see that the equation, like the solution looks like a parabola, which is great, right? And I can see that. So the slopes of these vectors on this side here are positive. The slope is negative, right? And this is negative, and this is positive here. And from here, you can see that you will have some slope vectors that looks like this. So it's going to be a straight line, go through -1 and -1 here, right? This is straight line, -1. It's just that at this point, if x equals to y, then you will have, so this points here when x equals to y, x equals to, not x equals to y, x equals to -y, because this is like a x equals to -y, like line. And then you can see that this is a solutions to this line right here. It's like y equals to -x, right? So that means when x equals to y, then your derivative should be equals to 0. And then if you look at these three differential equations, you have that this is this is the one that you want to have. Go to this one right here. You have when x equals to when y equals to 2, you have a equilibrium solutions. When y equals to 4, you have an equilibrium solution. Y equals to 0, you have an equilibrium solutions. So if equals to 2, then this right here should be your, this is in the third one, the third equation right here. And y equals to 4. When y equals to 4, the derivative equals to 0 and 0. So this should be the first one. And y equals to -x should be the second one.